Our speaker is Dr. Joseph Betzwieser. Dr. Betzwieser received his PhD in astrophysics from the Massachusetts Institute of Technology. Since that time, he joined the staff at Caltech and has been working on the Laser Interferometer Gravitational-Wave Observatory, also known as LIGO, where he analyzes the data for continuous wave signals, such as the ones that one might expect from rapidly rotating neutron stars. Dr. Betzwieser has also worked at Caltech on the development of the 40-meter interferometer prototype, and he is also joined tonight by a colleague, William Katzman. So I'd like to welcome both of them to the group tonight, and I'd pass it over to them now.
Thank you very much. Okay, let's see if I can work for this.
And while you're getting that up, Dr. Betzwieser, I'd like to let everybody know, as usual, if you have questions, please use the chat feature down at the bottom to ask those questions. But I think we're going to do something a little different. Dr. Betzwieser, you said as we take the virtual tour there, if people have questions, you might find opportunities to stop and let people ask them then.
Yep, the plan is to present some initial slides, do a kind of a tour in the middle of the control room, how we run things, go back to discuss some events, and then any final questions. I'm used to giving tours live when it's not pandemic times, so I'm used to people asking me questions while I do the tour. So I encourage people to ask questions in the chat, and then I think William will tell me verbally, because I'll be using the phone, which doesn't interact so nicely with the chat. Okay. Sounds good. Okay. So yes, I'm Joseph Betzwieser. I'm a staff scientist here at LIGO. I'm going to be talking about learning to listen to the universe with LIGO. I do want to say that LIGO is run by Caltech and MIT jointly, and is funded by the National Science Foundation. So without the support of the public for science, things like LIGO are not going to happen. So I thank you very much for your interest in astronomy and science in general. Okay. So why don't we get started with the talk? So LIGO is the Laser Interferometer Gravitational-Wave Observatory. So I want to emphasize that we are in fact an observatory. We are looking for astrophysical events out in the greater universe. We have two sites. We have one in Livingston, Louisiana, where I'm located. We also have another one in Hanford, Washington, separated by about 3,000 kilometers, or as light flies, about 10 milliseconds. And so we're a lot like a telescope, except we don't actually look for light. We look for events in gravitational waves. We look for astrophysical events like two black holes colliding or two neutron stars colliding. We're looking for basically some of the most violent events you can imagine in the universe, where you have things like stellar mass 10 times, 100 times the mass of the sun, orbiting each other and colliding at a significant fraction of the speed of light. These are the kind of like inspirals that can be detected here on Earth. What is a gravitational wave? A gravitational wave is literally a stretching and squeezing of space-time. If a gravitational wave were coming out of my computer screen straight at me, I would alternatingly get shorter and fatter and taller and thinner as the wave passed me by. It's a transverse wave. So basically, it acts in the direction perpendicular to its propagation direction. And so these gravitational waves are very weakly interacting. So let's say you have two 30 solar mass black holes orbiting each other, like that video was showing, and colliding. That very last moment, detected on Earth, let's say 1 billion light years away, is only going to change the length of a meter stick by 1 part in 10 to the 21. So basically, it's a very small effect, which is basically taken us something on the order of 45 years from thinking of how to do LIGO to actually doing the first detection, because of just the sheer amount of research and technology that had to be developed to make it possible to basically see the first event. In this case, back in 2015 on September 14th. I'm gonna try to mute myself, except I can't. I'll see if this plays. Hopefully people hear. People heard a background kind of hiss, which is the local noise of the interferometer, and that chirp sound was the astrophysical signal coming from a black hole merger, something like 1.3 billion light years away. So you might ask, well, how do you measure 1 part in 10 to the 21 of a length change? And well, we use a laser interferometer. So laser light has this nice property that the photons are kind of in sync. You can imagine them as electromagnetic waves with a high point and a low point. And as they're all lined up from a laser. They're all the same frequency, they're all the same wavelength, same difference, and they're in sync. So what you can do is send that laser beam to a special mirror that reflects 50% and transmits 50%, and then bounce them off mirrors. If the lengths between those two arms of those mirrors changes, it changes the interference back of the beam splitter. So the laser light goes down to the mirror and reflects off. It's got a certain phase that's come back. That high point meets with potentially a low point. If it does, you get destructive interference and no light comes out of the interferometer. All the light is reflected back towards the laser. If, however, let's say a gravity wave passes and changes the effective length of the arms by squeezing or stretching space-time, it changes the interference pattern out at our photodetector, where we actually make the measurement. So if we have a gravity wave passing, we see a light-dark pattern instead of a constant amount of light. Unfortunately for us, there are a lot of other things which could make the arms change their length, like scientists stomping around right next to the mirrors, bumping them, cars driving down the road, making the ground shake, or earthquakes somewhere in Chile, for example. So what we have to do is isolate those mirrors so they're kind of like free particles. So there's a whole bunch of technology that goes into making those test masses, those mirrors, be as isolated as we can from the rest of the world. So over here on the right is a suspension which holds the test mass mirrors. This bottom thing here is, let's say, one of those mirrors at the end of the interferometer arm. And what we do is we suspend it from a pendulum. Pendulums have this really nice feature that they isolate from high frequency motion. If you've ever played with like a yo-yo or a ball on a string, if you move it very slowly, the whole thing will move together. If, however, you move your hand very quickly, the bob, the thing at the bottom of the pendulum, moves much less than your hand. There's a special frequency where if you move your hand just right, you actually get more motion in the bob, called the resonance frequency. So above the resonance frequency of a pendulum, it isolates extremely well from motion at the top. And in fact, it goes as the frequency squared. So if you have a pendulum resonance of 1 Hertz, at 10 Hertz, you get a factor of 100 suppression. And at 100 Hertz, you get a factor of 10,000 and so forth. Well, in LIGO, since we figured 1 pendulum is good, 4 must be better. So we actually suspended 4 separate stages of pendulums. So with a 1 Hertz resonance, so instead of getting a suppression of 100, now you get 10 to the 8th, 100 million at 10 Hertz. Unfortunately, this also makes the control system a lot more complicated, where if you have a single pendulum, you have like 6 degrees of motion, up, down, left, right, forward, backwards. In this, you have more like 24, which makes it a much more complicated control problem for the instrument itself to keep the mirror still. Now, you still have the possibility of how you have to actuate on that mirror. In order to actually bounce the laser light down 4 kilometers and back, you have to be pointed extremely carefully. And in order to do that, we attach magnets, or we basically paint on electrodes onto the back of the mirror, so we could induce a static electric field and push off the mirror. If our actuator were attached to some kind of superstructure or other structure attached to the ground, you could imagine short-circuiting your isolation through your actuator. So what we actually do is hang 2 sets of pendulums. So we have 2 sets of quadruple pendulums, and we actually push off a second mass behind it, which makes the actuation much quieter, since you basically both are very quiet. And so for every action, there's an equal opposite reaction. When you push off one, they both move, and so you can control the position and pointing of the mirror. So this is our passive isolation. Now, as I said, pendulums don't do much below the frequency of resonance. So below 1 hertz, we don't really get any isolation. So this entire quadruple pendulum is hanging from a 2-stage active isolation system, which is shown here on the left, which has a whole bunch of sensors and actuators, which allows it to move 2 independent stages, basically in 6 degrees of freedom, so that when our sensor picks up a ground motion, saying ground, let's say moving to the left, it can move to the right to cancel the overall ground motion actively. So this is an active isolation system with 2 stages that we can move relative to each other. And then the whole thing is held up on a hydraulic system. So we can have a more range of throw in controlling the absolute position of the whole system. So we actually have 7 stages of isolation just to keep this single one mirror as still and isolated from the rest of the world as possible. On top of that, we then put it inside a vacuum enclosure and pump out as much air as we can, putting it down to something like 10 to the minus 8, 10 to the minus 9 torr, so that you don't have air molecules bouncing off the mirror and moving it around, as well as so you don't have laser light bouncing off the air molecules and getting scattered away from the beam path. So this is the seismic isolation system for a single mirror, which is already fairly complicated. Then we have a lot more mirrors. So there's not going to be a test later. I'm not going to go into extreme detail on this, but this is to kind of give you a sense of scale of how many mirrors we have in LIGO and how many degrees of freedom we actually have to control, often to within a wavelength of light, within a single fringe. In this case, we're using actually a 1064 nanometer laser light, 1 micron infrared, but we have to keep things basically within a fringe or a fraction of a fringe, a fraction of a wavelength on all these mirrors to make LIGO work. So there's an incredible controls problem associated with basically getting every single one of these mirrors into position so we can actually make the observing measurement. So what I'm going to do now is I'm going to try to transition to my phone and actually give a tour of the control room, which is where we actually run this interferometer from. I'm also willing to take questions at this point, while I transition.
I didn't see in that diagram anything called a laser being mentioned. Where's the laser in all that diagram?
Over here on the left. That?
I think you stopped sharing for a second.
Oh, sorry.
He couldn't see the laser, which you do need to do in order to do the transfer. But
let's see if I can share again. Sorry.
We can probably look later.
I've still got it up, so it's fine. So it's over here on the left. So basically, laser flows from the left side. I can go through this.
I got confused by all this stuff. I see it now. Thank you.
Yeah, this diagram is way too complicated to just kind of throw at people. I just wanted to shock people with the complexity and not actually have to read. I'm actually going to go through the tour and kind of explain how this flows. But yeah, basically it flows from the left to right and then out the far on the bottom. Okay, so I'm going to turn off my audio here and I'm going to stop sharing and see if this works. Audio.
now, as Joe goes around the control room, if you have any questions, you can throw them in the chat or throw up your hand, because you might have a question exactly about what you see. And so we'd like to capture the question when you have the question.
I have a question. Are the 2 observatories the only ones that are in existence today? And are there plans for others in the future?
I have some nice slides later which show where the other observatories are, but no, we are not. We have Livingston, Louisiana, Hanford, Washington are the LIGO lab. There's GEO 600, which is a 600-meter class interferometer in Germany. There's a VIRGO interferometer, which is 3 kilometer long arms near Pisa, Italy. There's the KAGRA effort in Japan, which is an underground interferometer, which is really cool. And there's a plan to put one in India using basically the innards from another LIGO interferometer. So there are 5 kind of big enough in theory to detect astrophysical signal interferometers, and there's a whole host of like smaller prototypes around the world.
Wonderful. Okay. And we do have a few other questions that came into the chat. William,
Sure.
I don't know if you want to handle those or.
Sure. You know what? I actually missed it, but so what other types of external noise do you need to do you have to deal with besides motion of the Earth, radiation, etc.?
Oh, we basically anything you could imagine getting into your electronics or moving something. So, for example, we actually have an entire group called that do physical environmental monitoring. So they measure things like electromagnetic fields, like from radio, monitor AC power lines. They actually go out into the LVA and play giant speakers and see how much sound is necessary to vibrate everything around, and see how that gets into the interferometer. So basically, anything that could vibrate the mirror, so sound vibrations, ground motion, and anything that can affect our electronics, lightning strikes, AC power dips, that kind of stuff. So
Related to that is, do you keep people at some distance when observations are being made?
yes, we do. The control room is actually a fair distance from the actual instrument itself. Like the actual instrument is about, in the direction I'm looking right now in the control room, I want to say like 100 feet, 150 feet, or something like that. So you have to literally walk down the hall, take a left, go right, and then go into a large vacuum equipment area. Ooh, I can actually probably just show you the video. 1 second. Enter. So can people see that? That is a camera inside our large vacuum and equipment area, which is over there, as I said. And so that, we don't actually let people in this area where the actual instrument is during our observation. You can kind of get a feel for the size based on, let's say, like that staircase over there. So we keep people out of there. We try to make it as quiet as possible in there when we're observing, which we're not right now. We turn off the lights. We try to turn off anything that makes any kind of sound. It's actually one of the quieter places I've been when we're observing. So yeah, you don't want anything near there. All our power into there, for example, is DC. All our electronics are DC powered in there. We try to get rid of the 60 hertz from the AC, which it still parasitically gets in, but we do our best to get it, to minimize it.
Daniel Roy is asking how small, what fraction of a proton do you actually measure to? Okay,
so our arms are 4 kilometers long, and the strain of, for example, from that first event was 1 part in 10 to the 21. So we're actually measuring about 1 part in 10. So basically 10 to the minus 18 meters. And if I remember correctly, a proton's got a diameter of something like 0.8 femtometers. I think that's 0.8 times 10 to the minus 15 meters. So yeah, we're a significant small part of a proton. So this is actually kind of the main plot we look at as gravitational wave scientists. And so that's kind of showing you the scale in strain. So that's like change in length over length. So that, what part, right? And so our spectrum, this is not live. This is actually this spectrum is from July 2017, that blue line. And you can see that's getting down to something like 10 to the minus 23. That's 1 part in 10 to the minus 23 is where the noise is at. So a signal, your signal noise ratio is related to that noise floor. So that the signal is basically in there, but that's kind of the scale we're looking at. So advanced LIGO, like in our last observing one, was able to get down to, at a certain frequency, something like 10 to the minus 1 part in 10 to the minus 23 over 4 kilometers, which is like 10 to the minus 20 meters. So yeah, much smaller than the diameter of a proton. Good, other questions?
There are questions about how many collisions have we seen and when was LIGO brought into service?
Ooh, how many collisions we've seen? I've actually literally lost count, dozens at this point. I have a nice slide, which is relatively up to date, which shows the number of mergers we've seen. So I can get to that later. What was the other part of that question? It was how many and when did we come online?
When did LIGO start?
Oh,
when did LIGO come online?
Depends on which version you're talking about, but
like LIGO was originally proposed back in the 70s by Ray Weiss. He wrote down like the initial equations that said what kind of noise that we see, like basically what the spectrum was going to look like. And then it was funded at various research projects to figure out how one would actually do this in the first place with technology. I think groundbreaking on the physical LIGO sites was late 90s. I forget the exact time. It was actually before I was in LIGO.
I believe 97, according to the plaque.
Yeah, I was still in high school at that point, I think. So groundbreaking here was in 97. Initial LIGO first lock was what, 2001? Oh, it's been a while.
Say the first run was 2002.
S1. I'm thinking that's like, depends on what you mean by like when was first LIGO after, because we didn't see anything basically through the 2000s with initial LIGO and enhanced LIGO. Enhanced LIGO would have been 2007. Basically, we kept upgrading the instrument, making it more and more sensitive until advanced LIGO, which advanced LIGO was basically first turned on in 2015. So that's the version. And basically during the engineering run, before our first observing run of the advanced LIGO detectors, which we've been basically putting back together after taking it apart to make it better for like 4 years. Before we even like went to the official observing run, the event came in. I was literally here kind of trying to get the calibration desperately in before the run started. And there was Anna Maria Effler and Robert Schofield were down at the end station doing some like PEM injection with some speakers or something. We've all decided to like kind of knock off at 4 a.m. because we're just all dead tired. And like literally an hour later, the first event rolls in. And that was back in 2015. And that started the period where we actually had detections. So if I'd been a little bit more workaholic, I could have prevented the first detection. So sometimes it's good to be lazy and go home at 4 a.m.
There's a question about what percentage of time do you observe versus maintenance and upgrade?
Versus maintenance upgrade. That is a good question. We've typically been doing lately, I want to say about a year's worth runs, and then we'll try to go down for a year or two and then do it again. The thing is, the range, the range you can detect out, range. The range you can detect things goes as the cube, like the volume you can see goes as the cube of your range you can see. And so if we can make a factor of, let's say, 2 improvement in sensitivity, if we can lower the spectrum that you see up there, if we can make the noise in the interferometer less by a factor of 2, that increases the volume by a factor of 8, which means you only have to observe 1/8 the amount of time to see just as much, just as many events. So there's always this tension between how much better do we think we can make it, and what does that mean in the event rate versus what we can get from the event rate if we just did nothing and just ran for now. And so lately, so let's see, I want to say we've been doing on the order of about year-long runs, and then we'll go down for, well, at this point, because of COVID, it's been longer than we really, really want, but we've been down 2 years from now. We're hoping, I think it was to have only been down for 2 years. It's gonna be a bit longer now, but I want to say 2015, 2016, it's been about even initially, but this is a much larger involved upgrade, which we're trying to do right now. So I want to say it's about even, but then let me put it this way, like the first observing run in advanced LIGO like saw 3 things, and I think we once saw 8 events in 02, and then I lost track in 03 because we were just getting so many. So the upgrades are worth it, but I want to say that's about it. Our observing time while in an observing run is actually limited by ground motion and other. Let me show. I could show you. Is limited by things like ground motion. So these are these sensors up here. These are reporting from ground motion sensors. And so if like you get an earthquake or something like a 6.5 earthquake in Chile or anywhere in the world, that will move the ground so much here that we can't keep the mirror still enough to actually make the measurement. So we actually have downtime due to things like hurricanes in the Gulf or something, raising seismic motion, earthquakes and that stuff. I think our net uptime was about 70% during the observing run. Forget the exact number off the top of my head, but it was something on that order. Hope that answers the question.
Since you're over by those graphs, there's a question about how much power consumption is used.
Are you asking about, okay, so the pre-stabilized laser that goes into the LIGO, we were running at about 50 watts of laser power, if that's what you're asking. I don't actually know what like our electricity bill is for the entire site, but the laser itself starts off at 50 watts.
I can tell everyone that the electricity bill for the entire site is the second most expensive thing we pay on a monthly basis. First is labor, second is electricity, and that's mainly for the HVAC. And I don't know what the total wattage is either.
Speaking of the laser, we actually have cameras looking at the pre-stabilized laser table, which is actually what these cameras are actually showing. So that's actually in air because we can't service it if it's in vacuum, and laser in vacuum is a bit more complicated. And that goes in through a window into the actual vacuum enclosure for the interferometer. But that is the pre-stabilized laser room, and that big box kind of in the middle of that is the main laser box. Was there another question? Sorry.
Yes, there's a bunch of other questions. Joe Dellinger asks about two things. So we'll go with his last question first, which is a really big quake like 2011 in Japan would probably knock you off for a while as the waves rattled around. So he knows that the earthquake showed up on some seismic stations for a month afterwards, and it excited modes of the earth that kept shaking that long. I think the basic question there is, how do earthquakes affect LIGO?
So earthquakes definitely do affect us. They don't usually knock us out for really long periods of time, but they can definitely knock us out for hours, especially on the really, really big ones, might be maybe 4 or 5 hours. It really depends on what frequency band those vibrations are in. Like the higher frequencies, we can do a better job of isolating, like human activity. And our active seismic isolation has certain frequency bands it does better and worse in. So we're not knocked off for like weeks, we're knocked off for hours. So basically an earthquake will come in and the operator will go get a coffee because he can't do anything right now. And then he knows in a few hours he's gonna have a lot of work to do to get all the mirrors back under control and back getting the light basically bouncing down the arms again.
Now, Joe asks another question, which is, how much did the previous iteration of LIGO miss being able to see events by?
Oh, good question. Would like, I have a graph on my computer which shows you the sensitivity difference between 01, 02, but it doesn't have the initial LIGO ones.
And it probably depends what you're talking about.
I want to say like factor 2-ish. Like the very first one we saw, like we only saw three in 01. So, but again, a factor of 2 is like a factor of 8 in volume. So it depends on what do you mean by which factor? Is like a volume factor, or is there like, so like that'd be like a factor of almost 10 kind of thing, depending on how you look at it. We'll oftentimes think in volume time quantities. I want to say that the sensitivity increase was at least a factor of 2 between initial and advanced LIGO.
Now, there's also a question just about what's the duration of an event between when an event occurs and when it's confirmed to be authentic.
That's an excellent question. So that's basically the data from here gets sent over to our clusters, our computer clusters, and then search pipelines get run on them. And those we have both offline and online looking at that data, search pipelines. The online ones can be very quick, like on the order of minutes, at which point they'll send an automated alert out to telescopes via the GCN network. And so those can be on, I want to say on the order of basically between event arriving and a automated signal going out is on the order of minutes. Getting verification of that in 01, 02, and 03 was actually the job of humans, unfortunately. We haven't quite gotten in the secondary authentication up. So what would happen is an event would come in at 3 a.m. People like myself would get a call, an automated alert. We'd wake up, go on TeamSpeak. We'd go look at stuff. We'd look at the, we don't have any up right now. The the data quality measurements, basically things telling us about the glitch rate, like how many like non-astrophysical like bloops and stuff that happen in the instrument on a fairly regular basis were happening, and stuff like that. We'd look at the data quality, look at what the other like physical environmental monitors basically, and say if the instrument was working in a good state or not. And that could take some time. What's a good example? Oh, for example, the GW170817, the one which was a neutron star event, took us about 4 hours to actually get an updated sky map out because there was a glitch just before the event in Livingston, which caused some problems with our gating of the data. So we had to kind of run stuff manually to produce the sky localization, which slowed everything down. So automated, if everything is going well, a few minutes. If there's something complicated, or if you want like a gold star, like, yes, we really think this is real, potentially an hour or two, depending on how fast humans work. Okay, other questions?
What's your favorite part of the job?
Oh, I mean, like the coolest moment, I think, was basically the day after the first event came in. It's like I was like waking up late because I'd been up working on the instrument. I walked in and it's like, hey, did you hear? It's like what? Like, we got an event, and that was like I don't know. At that point, I'd been working on LIGO for 15 years, 2001 through 2015. I've been working on this for 15 years without an actual detection. And we finally got that. That was awesome. On a day-to-day basis, it's basically the satisfaction of like actually solving problems, getting this giant convoluted mess of an instrument to actually work. It's very satisfying, basically, looking at basically seeing the events roll in, seeing us actually making measurable improvements to our sensitivity that improve our, what we often refer to as our in-spiral range, basically making the instrument better, and actually seeing what you've done is meaningful. So I like results, if that makes any sense, and seeing them.
There are a few questions which may go into the rest of your talk, but here's one that is asked that I don't think you cover, which is, does measuring gravitational waves tell us anything we don't know about gravity?
I mean, so far it's been consistent with general relativity, but there are alternative theories of gravity, which we've actually started to be able to rule out through our detections of gravitational waves. For example, the neutron star event, which was also seen in optical, let us rule out, to I think 1 part in 10 to the 15, the gravity actually, in fact, or gravitational waves, in fact, move at the speed of light. I mean, so based just on arrival time of the gamma ray burst versus the arrival time of the gravitational waves across 40 megaparsecs. And so general relativity has been holding up extremely well to every single test that's ever been thrown at it. So we are certainly learning to be able to rule out certain other alternative theories. But maybe we'll eventually come across something new that we didn't think about or didn't expect, which will teach us something new about gravity. But so far, general relativity is doing a pretty good job.
There's also a general question about public tours. And Joe used to lead a number of the public tours, but right now we're shut down due to the pandemic at both sites for public tours. We do expect to reopen, but when we'll reopen keeps being changed because the pandemic keeps shifting.
Yep. But I will be here when we do reopen. I like giving these tours.
We do have a number of other questions, but I think they actually lead into the rest of your
later presentation. Okay. I've completely lost track of time. So have I going to be going for about half an hour so far?
It's about right.
Okay. Let's see. What else did I want to go over while we're in here? Ooh. So when I said that this instrument was rather complicated, like this green screen is telling us a lot about like how many computers are in fact trying to run this instrument and how many channels that we actually record. So we actually have, what is it, channel FE? 245,650 channels associated with this instrument, basically sensors, like actuators, channels and stuff. So this entire instrument is a very complicated thing to run. And actually, I think since I'm here, I can show you, because I can, the brains of the instrument. So we have something over 20 computers running this instrument. Simply because we've got way too many degrees of freedom in this thing. I'm sorry, I'll try to go slower. I think I caught that. All right. Motion sick. Okay, in that case, why don't I transition to further on the talk if I'm making people motion sick. All right, I'm gonna stop sharing this guy. See if I can turn him back off. It's fine. Well, I can always come back to this later. I think I've shown. Ooh. Actually, wait. I did want to talk about the laser. I did want to talk about the laser real quick. So, some interesting things you can see while we're actually up and running, which is the pre-stabilized laser is at least running. Unfortunately, there's nothing on our mirrors right now because everything's shut down. But what you can see is this is our pre-stabilized laser. So we use mode cleaners all over the place. So the upper left says PMC trans. So that's actually our pre-mode cleaner transmission. So it's a nice round beam that goes through a special cavity. His entire job is to clean off weird shapes, which I don't know how well it comes through on my camera. You can kind of see there's like a donut shape with a hole on the left and a kind of a weird C-shaped things. That's what's getting rejected from the pre-mode cleaner because the laser has to be very stable, both in amplitude and shape as it goes into the interferometer. So it makes a nice beat note on the beam splitter and eventually the photodetectors. In addition, we also have a reference cavity, which we use as a kind of initial meter stick, if you will. It's a reference length cavity, which is temperature stabilized. And it's wrapped in like a big thermal coat, whose entire job is to basically stabilize the laser wavelength before we can actually start using the interferometer arms, which are a much better and more stable measurement of length. It's a ruffle cavity. Oh, so lastly, I will, nope, not that way. Let's see if I can go this way. I can show you pictures of that up here. These are fun. That is our pre-stabilized laser table picture. That big blue box is the laser. That big weird thing wrapped is the reference cavity. And I think I just saw that chat message, and yes, we do bad things all the time. If you have not actually made the interferometer lose lock, you're not doing real work. So usually that data will get flagged, but yes. So that's the laser table. So that's the source of our laser that then goes up that periscope, then goes into the interferometer, which then goes through various chambers, which I think I can try to show you real quick. These are what the innards of the LIGO and all those mirrors I was showing on that one diagram looks like when somebody takes a picture of them. And so just for reference and for tours, we have pictures of all the innards of the interferometer in the control room. And that's what's inside the vacuum equipment area. I also have pictures of people who actually do real work around here, like put stuff installed on, like me. Okay. I do calibration and software a lot. All right, I'm gonna switch over now. Okay, so I'm gonna turn this off, I hope.
We do have a question about, which I don't understand the question, so I'll ask you and see if you do. How much HPC do you have in the FLOPS? I'm guessing you're talking
high-powered computing? Like, is that like high-powered computing in FLOPS? Sounds like some kind of computer.
Yeah, it's flops.
Yeah, that's right.
I don't know. I like those are So are you asking like how fast the servers are?
Well, no, how much HPC do you guys have there? I saw all the racks, you know, in plots, how much you guys take to operate that thing?
Offhand, no, but I can tell you basically each of those computers is running like 4 to 5 real-time models, which are getting around the real-time calculation in about 64,000 times a second. So, and each of those round trips is basically a giant control loop. So basically a bunch of filtering and stuff.
Got it.
So, but yeah, it's non-trivial, but our searches in the big clusters take more. All right, let's see, how do I stop this? Cancel, stop video, there we go. And okay. Okay, can you hear me again?
We do.
I can disconnect audio on this one. That way you won't get an echo. Okay, good.
Question about the clock over your shoulder. And you're close. It's not January 1st, 1970. I want to say it was 1980, wasn't it? Number of seconds?
Oh, from when the GPS satellites went up? Yeah, it's something like that. I used to know this off the top of my head, but I haven't given a tour in ages, so I've forgotten. Yeah, but basically that's a GPS clock. So that's telling you the seconds since the GPS satellites went up. Share screen. Share sound, share. Okay. Slide. Okay, so I'm going to go on to the discussion of astrophysical events portion of this. And then again, I'll gladly take questions at the end of the talk. Okay, so. Oh, right. I did want to briefly go into, somebody had asked about I think somebody asked about the spectrum. I forget. This is showing the sensitivities of the advanced LIGO era. This orange color is the first observing run for advanced LIGO, which saw the first detection. And then we improved things in 02. You can see this improvement in sensitivity. This happens to be in meters per root hertz. And then 03, which this paper came from, which this black line is, sorry, measured noise in 03 is the blue line, is even further down at high frequencies. So that's kind of the improvement just in the advanced LIGO era. I want to say initial LIGO was like a factor of 2 above these, but don't quote me on that. I need to grab a spectrum, and it really depends on what frequencies you're talking about as well. Okay. I also just want to point out there's a lot of physics and physical processes which go into making that curve, including like, I think I'm running out of time at the rate I'm going, so I can come back to this if people have questions on the noise that makes up the spectrum, but I probably should finish the talk first. Also just be answering questions for the rest of the night. Okay. I want to talk about events. So somebody had asked me how many events we have. And this is a graphical kind of display of what LIGO has detected. So these blue dots are the LIGO VIRGO combined detections of black holes. So each time we have an event, we actually see 3 black holes, the 2 that started the merger and the 1 that we end up with. And you can see the purple ones are known EM black holes, which we know of because they're interacting in some way with something that can produce light, like they're accreting from another star or something, and thus we can see that light. But the interesting thing was, when we first built LIGO, we expected our first detections to be actually like these neutron star in spirals. This is one of the reasons why that range plot I showed you up there that like showed our sensitivity said something like neutron star in spiral, because we knew we had these gamma ray bursts, which we associated with neutron star mergers, and we kind of had a feel for how many of those. So we thought those would be the first things we did. And then we stumbled upon this huge population of black holes, which of really massive black holes. I mean, these are, most of these events are much larger than any of the black holes in the stellar range. So excluding supermassive black holes at the center of galaxies, but just like isolated kind of stellar class black holes, there's this huge population. We had no idea was out there until we could start listening to them in gravitational waves. And this is why I've said I've started to lose track of how many we've had, because it's starting to get it's like during 2003, the numbers kept going up every week. So we've also had neutron star black hole to black hole mergers. We've had 2 of those. We've also had, as I said, GW 170817 neutron star merger into just probably a black hole, but it's not absolutely clear what the final thing is. So all these combined lines is what LIGO has seen in neutron stars and black holes, and these purple and yellow things are what we knew from electromagnetic observations. Okay, what I also want to say is we can learn a lot from the waveforms of these gravitational waves. So not only do we learn that these things exist, we get the masses, and with the masses, we can then also determine the distance by itself. They make standard candles. So basically, the frequency evolution. So how quickly it reaches basically the in-spiral phase, or the in-spiral and then ring down. So how quickly it evolves in time tells us about the mass, which then lets us use the amplitude to determine the distance. So basically, every single one of these events is a standard candle. Kind of like how like a supernova 1A is like a standard candle. And so that lets us, if we have electromagnetic observations, let's say like in a neutron star case, lets us start like learning things about like the Hubble constant. We have another way to work out kind of like the astrophysical distance ladder. And so to kind of show that off, I'm going to go to our Open Science website. I hope everybody can see that. And what I'm going to do is hopefully this will come out and people will be able to hear it. So this is our first event, 150914, last part of the. It's a very quick boop. Let's go to a lighter detection. So this you can see is in detection band longer, and actually goes to a higher frequency. So it's got a higher pitch, whoop, whereas this is more of like a whoomp. And so that characteristic evolution is telling us astrophysical information. This is one that's in between those 2 masses. Now, this particular website these waveforms are showing off the cleaned up waveform. If you were to just listen to our raw data, it would just be a psh, which is what these things over here is the raw data that template has been searched for and found in. So for example, that crackle is effectively our noise spectrum converted to audio. And you need computers to basically tease out the signal. The very first one we detected was, we were lucky in that it was so loud, you could almost hear it in the raw noise. But halfway through. So instead of looking at pretty pictures for gravitational waves, so you can look at the waveforms, which I think are kind of really cool. Experiencing these things is actually often better done in audio. You can actually hear the differences. I think really cool. And anyone can download our public data and do all sorts of things with it. It's kind of cool to play with the data. All right. Somebody asked about the observatories around the world, and so this is a map. This is a map of our detectors. I said LIGO Livingston, LIGO Hanford are our US-based interferometers, the LIGO Lab, G600, VIRGO in Europe, KAGRA in Japan, and LIGO India's plan to use basically LIGO hardware in India. So one of the important things about multiple detectors is it lets us localize on the sky. Because this is like listening rather than pointing a telescope, since we're
essentially omnidirectional with different sensitivities in different directions. So because we're L-shaped, we're actually most sensitive to a gravitational wave coming straight down on top of us. And then if it's coming down one arm, we get like half the signal. And if it was exactly like 45 degrees, kind of zero signal. So depending on the polarization of the gravitational wave and the angle, we get more or less signal. But essentially, we don't have pointing from a single detector. So what we need to do is triangulation. We actually use time of arrival at the various sites to figure out where it's on the sky. So in events where we only have 2 detectors, like the very first one, GW 150914, we get like a big smear across the sky. However, in cases where we have 3 detectors, which will include VIRGO, we can do interesting things like GW 170814, and the really exciting one, which is the neutron star one, GW 170817, are much smaller smears in the sky of where we think the signal was coming from. And so multiple detectors let us pinpoint where these things are, in addition to improving the signal to noise of the overall waveform. So I keep referring back to this neutron star event, GW 170817, because it's my most favorite event, because it was not only seen in gravitational waves, it was seen in electromagnetic telescopes. Neutrino detectors were looking for it. It was seen by gamma ray telescopes. It was basically seen in everything. And because it was seen in everything, we learned a lot about neutron star mergers in this event. We'd never really caught a neutron star merger kind of in the act before, even though it was I think 11 hours after the event arrived, we had finally got a telescope had identified the progenitor location. But it was kind of a cornucopia of information, because you get things about like the Hubble constant out of it. You get things about like the masses of the kind of equation states of the neutron stars themselves, which is unclear exactly like what is the innards of these things look like and stuff. What I do also want to show is the difference in waveforms for a neutron star and small versus a black hole. They are very, very different. And let's see, why am I not having my mouse? 1 second. About why this. There we go. So initially, you're not going to be able to hear anything because this amplitude is too low. But you can already see that a neutron star event spends a lot of time in our band. And it's not a factor of like a few, it's more like a factor of 100. And so this leads to a very interesting possibility that we haven't been able to do yet. But you could imagine if we get better signal noise, you could detect this signal early on, like in the first 10 seconds, send an alert out. If it was fast enough, you could get it done in the next 30 seconds, and then slew telescopes to the sky location that are automated right now. I'm not getting sound. The thing about these events is that you can imagine in a world where you've got everything done just right, you can see the event early on before the merger, send an alert out, telescopes, and catch the actual moment of merger in an EM detector. Neutron star events are very distinct, different from the black hole mergers. A cute video which kind of shows how well we kind of localize relative to other options. So the event was first detected by was detected basically at the same time by gamma ray telescopes, Fermi or satellites. This is basically telescopes detecting gamma rays, and so they limited to an area like this. So LIGO Hanford, LIGO Livingston into the mix, we get this big broad flash. 2 seconds. You add in VIRGO, you get this much smaller area. And so telescopes, about 4 hours after it arrived, we finally got a sky map out. Telescopes started searching, and by 11 hours after first arrival, they were able to identify the host galaxy, able to see the afterglow from the merger. 11 hours from first arrival to finding it in EM. is a map of all the telescopes and satellites, basically, that were involved in that detection. It's basically, it was like there's like a quarter of all astrophysicists or astronomers were involved in the detections after the event. It was just so big in the astronomy community. Also led to all sorts of interesting science coming out of it. So, like, we now believe that many of the heavier elements that are here on Earth were actually generated in these merging neutron star collisions. Now that we've actually seen one, they've seen the spectra of the light off the ejecta off this, and you can see the lines for all these heavier elements and how much was generated. And you can start saying, maybe not all this was generated in supernovas, but maybe this is all being generated in these neutron star mergers. Supernovas are producing more of these lighter elements.
Are you saying the supernovas do not produce those heavy elements?
They don't produce as much. Let's put it that way. Like if you think about the colors on this diagram are trying to tell you the percentages you would think. So like much more uranium, for example, is being produced in these neutron star mergers we think now than in the supernova. There's going to be some produced because you have this energetic explosion, but it's nowhere near as much percentage-wise based on how many gamma ray bursts we see, how many supernovae we see, and those kind of calculations. So they are produced, but not nearly to the same scale, if that makes any sense. Yeah, so these various colored flashes are trying to tell you how much is produced in each method. Okay. Moving on. So LIGO is still getting more sensitive. We're improving the instrument, and we're hoping there's some things which we're expecting to hope to detect in the near, not too distant future. If we get lucky and a supernova happens while we're up supernova happens in our own galaxy while we're up and observing, there's a possibility it's asymmetric enough to produce a gravitational wave that could be detected here on Earth, which would be very, very interesting. We're also looking for continuous wave sources. So if you have an isolated neutron star, which is deformed just enough, it can produce a gravitational wave all the time at a very weak level. So if there's one that's deformed enough in our galaxy, and you take all the data we've observed so far, and you keep adding more and more sensitive data, you might eventually see this sinusoid coming from this neutron star, a steady clock essentially, that would tell us all sorts of things about the innards of that neutron star, the mass distribution in some sense, which could be combined with electromagnetic observations of, let's say, if it's a pulsar, with the pulsar timing information, how fast it's rotating and stuff, and we could get interesting condensed matter information out of such an event, or such a source, I should say, since it's a continuous thing. And we're still also looking for the unknown and unmodeled stuff. Like there's all sorts of theories that are potentially will show up in gravitational waves that might not show up in other ways. And we might also just run into things we've never actually expected to see before, simply because we've never listened to the universe before in gravitational waves. We've always been looking at electromagnetism, light, essentially, or like neutrinos, and this is a new way, and so we may just see things that just don't show up in any other method, like black holes. We're also looking for a potential stochastic background of unresolved sources. So you could imagine weaker sources, but there's more of these, maybe lighter black holes, very, very distant, could produce an astrophysical signal that's in our detector that looks like kind of random noise, but is actually astrophysical in nature. And if you cross-correlate between detectors, you can actually tease that out of the information, out of the detectors. You might not know any given one, but it'd be like looking at a very dense star field where you can't actually identify any individual star, but you know there's a bunch of stuff that's there glowing. So we're still trying to make the instruments better, trying to get more events, and trying to see more new kinds of events as time goes on. That's the end of the slides I prepared and what I want to talk about, but I would gladly take more questions. Also, I'll leave up here for the resources, which are some interesting websites people can go look at. Basically, LIGO Scientific Collaboration Outreach, as well as LIGO Lab Outreach, the Open Science website is where you can actually get the LIGO data. You can play with it yourself, and they have some nice tutorials and educational resources there as well.
Okay.
And Dr. Betzwieser, you also mentioned that we can buy logoed apparel for the LIGO Observatory as well, right? T-shirts and whatnot. So
William has the information.
I know it's not on this link, but it's still fresh on my mind. I need to get that ordered.
Yeah. Maybe William can like put a link in the chat or something. I don't know.
I'll look for it.
Okay.
I'm actually caltech.edu, their gift shop, and Cafe Press are the two main sources. But I'll actually look for the links and try and throw them in.
Thank you.
Thank you. That'd be great. I guess I should start reading back through the chat because I haven't been paying any attention to it.
You know what we might just do is ask if anyone had a question in the chat that wasn't basically answered, because there were questions that were like, how do you know the difference between them? And I think you hit those, but did anyone throw a question in the chat that hasn't been answered to their, to what they were thinking?
If you do, go ahead and come off of mute and feel free to ask your question of Dr. Betzwieser.
Please do.
Yeah, so I've studied ocean noise, so I know about like dB per root hertz and a unit per root hertz, et cetera. So I'm curious, all those spikes in your data, how many of those spikes have you figured out what's causing it, and how many of them are mysterious?
Oh, that's a great question. So you're talking about like this spectrum,
Yeah,
right?
look at all that.
Yeah. So let's see if I can identify something. So 60 hertz, 120. Oh, sorry, 60.
Yeah, those are obvious.
That's AC. We have calibration lines at very low frequencies. So this thing here is me taking a special laser at the end station, which we run basically all the time, and shooting a 2-watt laser at the mirror. Like the circulating power for the main beam is something like hundreds of kilowatts of laser power in observing. But we take a beam at kind of not quite 45 degrees, but basically kind of off axis. We bounce it off. We have a photodetector on the other side, and we measure how much photons we're bouncing off of it. And so we can induce by radiation pressure motion in the mirror from that laser. And since we know how many photons bounced off, we know how many newtons we're pushing on it. We know the mass pretty well, 40 kilograms. And since we know that the exact mass, we can actually calculate how much oscillation we induce. So it's a modulated laser beam.
Okay, cool.
So that's what this low frequency stuff is. High frequencies up here, you know how we hang everything from a suspension?
Yeah.
What happens when you pluck one of those things? It rings like a stringed instrument. So up at like 500 kilohertz, these are violin modes, as we call them. It's basically a ringing of the suspensions.
Okay.
So
cool.
a lot of these really big vertical lines, we do know what they're coming from. They're like some variation of some kind of calibration signal in some loop. They're resonances of some structure or other. And then this plot is actually telling us what we think is the underlying noises that add up to the overall thing. And the difference between the black and the blue is what we don't know, if that makes sense. Black is the sum of all the noises that are on this particular plot, and blue is what we actually measure.
Well, in ocean acoustic data, when you see lines like that, it's often like ships going by. So I wonder if it's like some alien starship powered by gravitational waves going by. That's the propeller on the alien gravitational starship.
The problem is gravitational waves are just so weakly interacting. It's like you'd have to be crazy to use them to do anything. It's like you got to move like black holes to like do anything real, man. If you can do that, I feel like there's like easier ways to do it. But yeah, like our job as instrument scientists working on site is to try to make this plot as low as possible and to get rid of as many lines as we can.
Yeah, it's amazing. Okay, cool. Thank you.
Yeah, no problem.
All right. Who else has a question and wants to come off of mute and ask it?
Yeah, I wonder, you guys have a heck of a seismometer here. Is the closed loop system that allows you to isolate from the seismic movements, is the closed loop data used by the geologists? Because you have a heck of a seismometer here.
Oh, interesting. Yes. Well, the thing is, most of our sensors are not actually on the ground. Like we have some on the ground, but most of our sensors are actually on our like isolation stages, and we're trying to isolate them from the ground as best we can. So we're actually, you want a device which was down, like we do actually share, I believe we share our seismometer data that's actually on the ground, but like everything that's actually on the instrument is useless because we're trying to isolate it from everything else. So the fact is we're attenuating everything. So if we're seeing it, seismometers have seen it a long time ago, if that makes any sense. We are doing our best to, like, in our ideal world, you could not use our data for seismometer purposes because there would be nothing there. We would be perfectly isolated. So I believe we do share our seismometer data, but like the rest of it's kind of worthless to ground motion type stuff.
All right. Any other questions? We have time for maybe one or two more. Is that okay with you, Dr. Betzwieser?
I'm fine. I can go all night.
Okay.
You guys probably want to quit.
No, we love this. This is absolutely fascinating. Give another second or two to let people ask questions.
Look at chat, see if there's anything. I try to be entertaining. I feel like I'm just reading the chat. Like, I feel like the job of a scientist is we have to do outreach. Like our entire job is to gain knowledge and then share it. Like if we don't do the second part, there's no point.
Right.
So I'm always glad to do this kind of thing.
And we appreciate that. Thank you. Okay, any other questions? One came in from Wayne Turner. Is there any kind of background gravity wave noise like the microwave stuff?
That's kind of like that stochastic background I was saying. Like in principle, potentially there is something out there. We have not seen one yet. I mean, in theory, there are, like, you could have primordial black hole producing stuff, or how's it go? I think there's supposed to be something from potentially the inflationary era. I'm more of an instrument scientist rather than a cosmologist. So it's what I've come across and not necessarily studied in depth. I used to know astronomy really well back in like 2007 when I was taking my general exam at MIT, and then ever since that's been downhill. But oh, sorry, didn't get overlaid. Sure, I can put that up while I'm talking. But so in theory, yes, we haven't seen one yet. Oops.
And it's not caused by the microwave oven like it was at I think it was the Parkes Observatory. Right?
Well, no, I mean, we tried. There was one time somebody left the PSL phone on, so we're supposed to like turn off all the electronics in there, and like it rang, and like somebody was like listening to the Gravitational-Wave channel. Why does this sound like a phone? Like a little, because it's an audio transfer, right? I mean, it's audio band. If you're listening to it, you say that's a phone. And it was directly modulating our laser power because it was in the pre-stabilized laser room. So we do our best to eliminate those things. So
right.
But yes, there are some funny stories out there.
All right. And any last questions before we wrap up for the evening? We had quite a few come in through chat, so I really appreciate the interactivity and the opportunity for folks to ask those.
Oh, no, I mean, this is how I give tours. I view this as a virtual tour. So
yeah.
I'm used to like small kids coming up to ask me crazy questions like, what's your innards when you fall into a black hole? I mean,
okay, well, I'm not hearing anybody ask. Dr. Betzwieser, thank you so much for taking the time today. And William, you as well. We really appreciate you both joining us tonight. This was very informative, just a great glimpse into a lot of the great science that you all are doing out there. We are really excited for everything that you're doing and wish you continued success as you continue to discover some of these awesome things that are in our universe. So thank you very much. And we're hoping that sometime soon, once this pandemic sort of abates, subsides, we're hoping it does, that we'll be able to actually make a field trip out there. That was something that we planned a couple of years ago, but we're looking forward to the opportunity to do that and make that trip someday soon. So thank you very much for joining us this evening. We really appreciate it.
well, thank you.
Okay, and I will share my screen here just for the closing, if you don't mind.
Yep, I think I stopped, and I'll mute myself.
Wonderful. Okay, thank you. All right, well, that wraps up tonight's meeting. You can see my screen there. We have next month's meeting Thursday, November 4th, and our novice meeting, I should say. And our general meeting is going to be on Friday, November 5th, Hey, it's my birthday, so I'll be spending my birthday with everybody else here. That's something I couldn't imagine a better way to spend the birthday. But we also have our annual election, so please try to join us for that meeting and participate in the process of electing your officers and leaders of the club. And if you're interested in a position here in the club, please throw your name in the ring. We'd love to have you join our leadership ranks. So again, thank you very much, Dr. Betzwieser and William. Certainly appreciate the talk tonight, and we'll see everybody soon. Thank you. Stay safe, everyone.